Hello. In this video we will be having a basic look at the inertial navigation system, which is incorporated in modern airliners. Whilst GPS and other beacon information is usually used by the aircraft, there may be periods of time where these are not available. Therefore, we need a backup navigation system which is capable of operating without the need for external information. An inertial navigation system, or INS for short, is a navigation technology that determines an aircraft's position, velocity, and attitude, using accelerometers and gyroscopes. It works on the principle of inertia, which states that an object will continue to move in a straight line at a constant speed unless acted upon by an external force. We will now look at the various components of the system. Accelerometers. INS utilizes a set of accelerometers to measure the linear accelerations experienced by the object in various directions. An accelerometer is a device that measures acceleration forces acting on an object in 3 dimensions: up and down, side to side, and forward and backward. It works based on the principles of inertia and the movement of tiny mass spring systems. Here's a simplified explanation of how an accelerometer works. 1. Inside the accelerometer, there is a small mass suspended by springs. This mass is designed to move in response to external accelerations. 2. When the accelerometer experiences an acceleration, the mass wants to remain stationary due to inertia. However, the springs surrounding the mass resist this motion, causing the mass to compress or stretch the springs. 3. The compression or stretching of the springs generates an electrical signal, usually a voltage, which is proportional to the applied acceleration. The electrical signal is then sent to a processing unit for further analysis. In modern accelerometers, the electrical signal is generated by the mass being surrounded by piezoelectric crystals. As the mass moves, there is a force applied to the crystal, which causes it to deform slightly. This deformation induces an electric charge proportional to the applied force. The processing unit interprets the electrical signals to determine the magnitude and direction of the acceleration. It can provide measurements of acceleration in all 3 axes. These accelerations are integrated over time to obtain the object's velocity. By further integrating the velocities, the system calculates the object's position relative to an initial starting point. Gyroscopes. On this YouTube channel there is a video that describes the basics of how a gyroscope works. Therefore, we do not intend to go into depth on the theory in this video. Suffice to say that gyroscopes maintain their attitude relative to space, and therefore can be used to measure angular velocity and rates of turn. Gyroscopes in the INS measure the rate of rotation, or angular velocity experienced by the object, in 3 axes. By integrating these angular velocities over time, the INS determines the object's attitude or orientation. Modern inertial systems use a ring laser gyroscope, which is more accurate, and contains no moving parts. This YouTube channel contains videos that describe how a gyroscope is used in flight instruments, such as the turn indicator, the direction indicator, and artificial horizon. These videos will give further information on how a gyroscope is used to determine turn rates, heading, and attitude information. The INS gyroscope does the same thing. With both the accelerometer and gyroscope information, the INS will determine several parameters. These parameters include heading, position, and aircraft attitude. These parameters are then sent to the computers that provide flight instrument display information. The PFD will display the aircraft attitude and heading, and the navigational display will display heading, track, and position information. INS provides continuous and autonomous navigation, making it highly reliable without relying on external references or signals. It does not require GPS or beacon information once it is running. However, it does require an initial position to be entered prior to flight. This position can be entered either by entering the position on the flight management computer and/or dedicated panel, or by taking the accurate position from the GPS system. If the GPS is not available, such as an area where jamming is occurring, then the position is entered via the keypads. The pilots have access to charts which give the latitude and longitude of parking stands. The pilot then enters the position of the stand or parking bay where the aircraft is parked. Once entered, the INS then works automatically from then on. Errors. As the INS uses accelerometers and gyroscopes, errors will creep into the system. As described in the gyroscope video, available on this channel, over time the accuracy of the system might degrade. To mitigate this, INS is often integrated with external navigation aids like GPS or other sensors, such as VOR and DME beacons, to periodically update and correct its position and orientation. If these aids are not available, the pilot may have to enter an updated position manually. However, inertial navigation systems also incorporate sophisticated mathematical algorithms and filtering techniques to enhance their accuracy and stability. These help compensate for errors, and INS generally remains very accurate for the purposes of aircraft navigation. To sum up, the modern airliner can navigate the world's airways using the inertial navigation systems. It can do so without any input from GPS or other external beacon information. It also provides accurate data for attitude and heading displays. Thank you for watching.